Here, x is a continuous random variable. It has PDF, probability density function, f of x. The expected value of this random variable is defined as e of x equal to integral the lowest possible value that is in the range of x to the largest possible. X min could be minus infinity and x max could be infinity. X times f of x dx. So let's take a look at some examples. F of x is 2x and x is between 0 and 1. Well, the expected value of this random variable is 0 to 1 x times f of x, which is 2x dx, or integral 0 to 1 to x squared dx. If you calculate this analytically or using some software, you find that that's equal to 2/3. So let's look at the interpretation of expected value of x. We can start with a PDF, which is just a constant. So let's say that the range is from 0 to a, where a is any positive constant. And let's begin with the case where every x in this interval 0 to a is equally likely. That may sound like a strange concept since the probability of each outcome in the interval is 0, but what we mean by equally likely for a continuous random variable is that the PDF is constant. The integral over the interval of f must be 1, so this constant must be equal to 1 over a. So it now looks something like this. We see that the integral of f of x is 1 over a times a, which is 1, which is supposed to be. In this case, when all the x's are equally likely, then the expected value of x is simply the average of all the x's in this interval 0 to a, or right at the middle of this interval, a half. That will be the expected value of this random variable. That's easy to show because expected value of x, by definition, 0 to a, x times f of x, which was 1 over a dx. If you plot this, you'll get a triangle with base equal to a and height equal to 1. So this value is precisely a over 2. So again, you can think of the expected value as the average of all the x's. So let's generalize this. Let's now consider an example where f of x is not constant. The x's are not equally likely, but we keep the range to be from 0 to a. So I have my f of x, but now it's not constant. Maybe it looks perhaps something like this. The area is still 1. The way you can think about the expected value of this random variable is as the weighted average of the numbers between 0 and a, and the weight is determined by f of x. As f of x is high in the right region and low in the region close to the origin, we put more weights on the x's close to a, and that means that in this case the expected value will be to the right of a half. So if this is a by 2, then the expected value may be somewhere here. It's hard to say exactly, it depends on what f is. Here's another way you can think of the expected value. So let's look at another example with an arbitrary range. Let's say I have some PDF which looks maybe something like this. So my x min and my x max. If you mark the area under the graph like this, and imagine that you make a cutout of this particular area using some sheet of metal, which is completely uniform. The expected value of the random variable will then be precisely the x-coordinate of the center of mass. So let's say that the center of mass is here. If that's the center of mass, then just by going down to the x-axis, we can find the expected value. So you can think about it as this particular object being balanced right at this point. If we look at this example again, the one with f of x being 2x with 0 x1, then this PDF looks something like this. And we found the expected value to be 2/3, 0.667, maybe somewhere around here. And that will be precisely the center of mass of this object. One final example. The PDF of the standard normal distribution. If you draw this PDF, it looks something like this. It's this typical bell-shaped curve. This curve is completely symmetric around the y-axis. So the center of mass is right at the origin, right here. That means that we can just look at the PDF and conclude that the expected value must be 0. You can of course confirm that by calculating x times f of x, in this case from -infinity to infinity,